Hello and welcome to the screencast for Chem Activity 21, Predicting Binary Reactions. When will precipitation or neutralization reactions occur? This is Dr. Michael Garut, and this is a screencast recorded for Allied Health Chemistry, Chemistry 120 at Missouri Southern State University. So here's where we are in the schedule of the units of the class. We're in the middle of the third unit, and we have just finished the Activity 20A, Mass Relationships, Stoichiometry. So we still have binary reactions, oxidation states, redox reactions, and equilibrium before quiz number 3. Believe it or not, we are actually more than 1/3 of the way through the class at this point. 1/3 of the way through the chem activities for Chem 120. That's good news, right? Okay. Critical thinking question. So this is strange. This activity doesn't have a model at the beginning. It starts straight with questions. That's probably because, in this case, these questions are applications from previous activities. And that is the case here. We're applying things from previous activities. These are writing the formulas for compounds. That's naming. You'll remember that on Blackboard you can download this handout that gives you, that's kind of the cheat sheet, Cliff Notes version of remembering the naming that we've learned so far in the class. So if you need to have that beside you to do that, that's fine. Of course you don't get it on the quiz, but you do. You can use it at this point or on the homework. How to name ionic compounds, how to name acids and bases, and a list of polyatomic ions to memorize. So what I'm going to do here is every 3 or 4 seconds, one new compound formula will appear. You should do them one at a time. Compare my answers with yours. Each time that you see that yours doesn't match mine, pause the video, try to figure out what it is that you missed, and then unpause and go on with the next one. So one will appear every 2 or 3 seconds. Here we go. Barium nitrate. Barium is +2, nitrate is -1, so 2 nitrates to go with 1 barium. Sodium acetate. Sodium is a +1. Acetate is this ion, and it's a -1, so you need 1 of each. Magnesium chloride. Magnesium is a +2, which you know because it's in the second column of the periodic table. Chloride is a -1, and so you need 2 chlorides to go with 1 magnesium. Sodium hydroxide. Sodium is a +1, hydroxide is a -1, and so 1 of each. Calcium phosphate. Calcium is a +2 because it's in this column. Phosphate is a -3 because you memorized it. And so in order to make that work out, we need 3 calciums at +2, 2 phosphates at a -3, so that you get a +6 and a -6 canceling out. Lead 2 sulfate. The 2 tells you that lead has a +2 charge. Sulfate, you memorized, has a -2 charge, and so 1 of each. Sulfuric acid is H2SO4. This is just one of those things you memorize, or you've memorized that sulfate is SO4 -2, and when you add 2 hydrogen ions with that to get H2SO4, that you change the ATE to the IC, so sulfuric acid. Here's another thing. This will be fun. Johnny was a thirsty child. Johnny is no more. For what he thought was H2O was H2SO4. Yeah. Sorry. My kids love my bad dad humor, and now we got chemistry humor and dad humor. It doesn't go well. Sorry. All right, move on. Draw ammonium carbonate. Ammonium carbonate, NH4CO3. Is that right? Ah, not quite, right? Ammonium is NH4 plus, so I need two of them to go with carbonate, which is a CO3 minus 2. That's a strange one. We haven't often seen the parentheses around the first one before, but ammonium is the only positively charged ion that we've seen that makes salts. So there's ammonium, there's carbonate, and so we need one ammonium to go with two carbonates. Ammonium carbonate. That should be review. Now we go on with Model 1. These are solubility rules for ionic compounds. So back when we first learned about ionic compounds, we said we would not learn how to predict if an ionic compound was aqueous or a solid, whether it was soluble, until later in the course. Well, now is later. So it's time to make those predictions. What's happened is that chemists or just experimenters have mixed all sorts of compounds together to see which ones dissolve and which don't, and come up with a list of rules that summarize that up. So this list of rules, it's good to commit some of it to memory. However, this list of rules is on your exam cover sheet. So in addition to the periodic table, here's your list of solubility rules. So that's something that you're allowed to use on exams and save your brain cells for learning how to apply them rather than just memorizing them. So here's your list of solubility rules. You don't have to memorize them. And of course it says right here, you need not memorize this information unless your instructor requires it, and I'm your instructor and I'm not requiring it. So there we go. Question 2. Recall and record the meanings of the phase labels A, Q, S, and L. Pause the video and write those into the space. Okay, so AQ for aqueous, S for solid, L for liquid. I've written the L kind of cursive there. Otherwise, you can't tell when I'm writing it whether it's a 1 or an L. So I've written it like so. Okay, number 3. Suppose that each compound in question 1 is placed in water. Examine each rule in Model 1 in order. So what you're going to do is go down the rules in order. When you reach a rule that applies to the compound, place the symbol AQ or S after the formula to indicate its solubility in water. So I'll just do the first one for you. All right, barium nitrate. So barium nitrate, if I can get this just right, I can get all the rules. Well, that's as good as we're going to get. All of the rules, except for Rule 5 off the bottom of the screen that says any other compounds are likely insoluble. So, barium nitrate. Rule 1, a compound containing a cation from group 1. Is barium in group 1? No, here's barium. It's in group 2, so that doesn't apply. Or the ammonium ion is likely soluble. Okay, well this compound doesn't have any of those, so let's move on to rule number 2. A compound containing an anion from group 17, the halides. That would be fluoride, chloride, bromide, iodide. Nope, it doesn't have that. So let's go on to rule number 3. A compound containing nitrate. Aha, this compound contains nitrate or acetate is likely soluble. Okay, so that rule applies. Soluble means it dissolves, so I put AQ. See how that works? So now just go down the list like we did before, apply the rules, put S or AQ after it, and every few seconds or so, the answer that I think it is will appear. Start with sodium acetate. Pause now. Okay, this one you got to on rule number 1, right? A compound containing a cation from group 1, aha, that's sodium, is likely soluble, so I put AQ. All right, I'm going to give you a hint. In the remaining questions in number 1, there are only 2 that are solids. So that's my hint. Go ahead and do all of C through H, and then all of those answers will appear, and you should only find 2 that are solids. Go. Okay, which 2 are solids? Calcium phosphate, because no rule applies to calcium or phosphate, so you get to rule number 5, which says any other ionic compound is likely insoluble, and that means a solid. And then lead sulfate, lead 2 sulfate. That's rule number 4, which says a compound containing sulfate is likely soluble. However, there's 3 exceptions: barium, mercury, and lead. Lead, so that's an exception, so that's insoluble. And I went ahead and wrote which rule applies. Notice that H2SO4, sulfuric acid, is not an ionic compound, so I couldn't choose a rule from that. But remember, that's on our list of strong acids, and strong acids are strong electrolytes, and strong electrolytes are split up into ions surrounded by water. So that's an AQ. Moving on to the next section. Recall that binary compounds that dissociate into ions when dissolved in water are referred to as electrolytes. Chemical reactions between binary compounds occur whenever 2 electrolytes can combine to form an insoluble solid or a covalent molecule such as water. And here are 2 examples. When you can produce water, an acid plus a base giving you a salt plus water, that's called a neutralization reaction, also an acid-base reaction. And when you can form an insoluble solid, a precipitate, that's called a precipitation reaction. So those are 2 types. Some textbooks will go into gas-forming reactions here. Those also form covalent molecules, like carbon dioxide. And so if you see that somewhere, that also fits in this category. But I'm not doing the gas-forming reactions, just precipitations and neutralizations. So Model 2. There's 2 reactions. They are balanced. You can double check and make sure that's true. Question 4. What insoluble solid is formed in reaction 1? This is it, right? Silver chloride, or silver 1 chloride, if you like. And then consider the information on the previous page. What type of reaction is this? So we've got 2 types, neutralization and precipitation. This one would be precipitation because it produces an insoluble solid. Okay, now you do this for number 6. Fill in both of your answers for number 6, and then my answers will appear. Pause the video now. Okay, I think you got that one. Number 7. What 2 cations are present in the reactants in reaction 1? So the reactants in reaction 1 are these. And what are the 2 cations? Pause the video and record your answers. Alright, so if you wrote this in words, you would just put silver ion and sodium ion. Since I wrote it with symbols, I needed to put plus and plus to get the right charge. You might have put the AQ after it. I have not done that here, and that will you'll see why later. So go ahead and pause the video and answer question 8. What 2 anions are present in the reactants in reaction 1? Pause now. So we have nitrate and chloride, both with a -1 charge. Correct? All right, pause the video and answer questions 9 and 10, which which refer to the products of reaction 1. Pause now. So they're the same, right? Silver and sodium, chloride and nitrate, and those are the same as in 7 and 8. Question 11 says, discuss the changes that the silver ion undergoes as reaction 1 occurs. So if I page back down so that we can see it. Okay. We started with this, silver nitrate aqueous, and then we ended with this, silver chloride solid. So write a sentence that describes what's happening to the silver ion. Pause the video and write your sentence now. So if I look at the cations here at the beginning, I have silver and it's aqueous. If I look at the cation at the end, it's still silver, but now it is bonded to the chlorine and it's a solid. So in my sentence, that's what I wrote. Aqueous silver ion makes an ionic bond with aqueous chloride ion. I didn't mention that, but aqueous chloride ion is also there. And precipitates as an insoluble solid. And I guess I could go ahead and write there AgCl. Now if you didn't say silver ion was aqueous at the beginning, and you didn't say it made an insoluble solid at the end, do you understand why that's the case? Why it was aqueous at the beginning, meaning surrounded by water, but at the end it's now attached to the chloride and that precipitates out. So if you don't have something that indicates those features, pause the video and edit your answer to number 11. And while you're paused, go ahead and then answer question 12 about which changes the nitrate ion undergoes. Pause now. Alright, so now you're writing what happens to the nitrate. Nitrate starts out aqueous and it ends up aqueous. So that's what I've written in my sentence. Aqueous nitrate ion remains aqueous, which means surrounded by water. In other words, nothing changes for nitrate. So there's a big difference. Silver ion starts out aqueous but becomes part of the solid silver chloride. Aqueous nitrate ion has no change. Why did we even say silver chloride was a solid? We go back to our rules. And when we get to rule number 2, a compound containing an anion from group 17, the halides, that's chloride, is likely soluble, but silver is an exception. So that's why silver chloride is the solid. That's why we wrote silver chloride as a solid here, and that's why we can write this sentence, which says that silver ion makes a bond with chloride ion and precipitates out. So, making a list of steps needed to predict the products of a precipitation or neutralization reaction from this model. So go ahead, pause the video, and make yourself a list. Then you can compare your list with what I have. Pause now. Alright, so here's my list. Yours might be similar. Make sure that it is essentially the same. I just said, first, determine all the cations and anions. Second, I said swap the cations and anions to see what compounds they might make. And 3, I said determine if these possible compounds that we did in number 2 would produce a solid or a molecule. In other words, when I have all the cations, silver, nitrate, sodium, and chloride, if I can swap them to make other compounds, I can only put positives and negatives together, right? So I can't, for example, put silver with sodium. 2 positives wouldn't bond together. I can't put nitrate with chloride. 2 negatives wouldn't bond together. But I can put the silver with the chloride and the sodium with the nitrate, and that's the possible new products that could make. And then I need to see if those make a solid, or such as silver chloride, or water, a small molecule like water. When I do that same sort of thing here, well, nope, don't have anything there. So let's talk about that one for the calcium hydroxide. And let's apply that. What are the possible ions? We have calcium ion, that's a positive 2, and OH, we don't put like this. Hydroxide ion doesn't stay stuck together, so it's hydroxide ions, which is a negative. There are 2 of them. I could put 2 of them out there, but I'm just writing the types of ions that there are. Over here we have HCl, which we know is a strong acid and dissociates into ions H plus and Cl minus. So that was my step 1, determining the ions. Now recombine them to see if they can make any different products. Well, when I recombine the calcium with the chloride, I get calcium chloride, and when I apply the rules for that, it's still aqueous. When I recombine H plus with OH minus, do you see what that makes? An H plus with an OH minus, that makes HOH. Well, what's HOH except H2O, right? So if I can make a solid or water, then I can get a precipitation or neutralization. So look at my list of steps. Pause the video and make sure that your list of steps is essentially the same and that you understand from your list of things how to do each of these kinds of reactions. Once you've done that, then you're ready to apply it. So we're going to go on with 14. Write the formulas for the 2 products that are possible when silver nitrate reacts with calcium bromide. And then part B, write and balance a chemical reaction for this solution. So pause the video and do both parts A and B. Pause now. So I did part A. I come up with AgBr as a possibility. You didn't put this, did you? AgBr2? You might have said, oh, Ag and Br2 go together, but why doesn't that work? It doesn't work because silver is a +1 and bromide is a -1. So when we make that formula, it has to just be AgBr. Similarly, we can't just have Ca with an NO3. Ca is a +2. And nitrate is a -1. So since I have a -1, I need to have 2 of those nitrates to go with the calcium. Does that make sense? Whenever you build ionic compounds, just like we've learned, you have to make the charges balance out so that they neutralize. Alright? Pause the video or just wait 2 seconds and this chemical reaction will appear. Alright, I didn't actually finish the reaction, but I got it started. Silver nitrate, aqueous. Calcium bromide, aqueous. How do I know those are aqueous? I apply the rules. Nitrates are soluble, bromides are soluble. That would be Rule 3, nitrates are soluble, and Rule 2, halides are soluble and not an exception. Then I would do the same thing for the products. Nitrates are soluble, so that's AQ. Bromides are soluble, but silver is one of the exceptions. Right? A compound containing an anion from group 17 is soluble, but an exception for silver. So that's a solid. Now I have the formulas for the products. I could have figured that out here on number 14. I could have said solid and aqueous. Right? I need to balance this equation. So 1 silver, 1 silver. I can balance nitrogen and nitrogen, but a shortcut would be, let's just balance the whole nitrate, because the nitrates stay together. So nitrate, NO3, oh, there's 2 NO3s, so let's put a 2 out here. Now I have 2 NO3s, which means I have 2 nitrogens and 6 oxygens, but this is also 2 nitrogens and 6 oxygens, so that's kind of a shortcut. When I've done that, though, I've made 2 silvers, so now I need to put a 2 here to make 2 silvers over here. That makes 2 bromines. Oh, but that's good because I already have 2 bromines. On this side, calcium is 1 and 1, so now it's balanced. What I can't do is balance it by, right? I can't just do this to balance bromines, right? Because that changes the formula and then they don't balance out to make 0 charge. So when I'm balancing, I only change the coefficients. Did you get this? If you did, great. And if you didn't, you get another chance. So now on 15, you're going to go ahead, add in the AQ and S and L, and then decide if this reaction occurs. Pause now and complete question 15. So I got aqueous, aqueous, solid, and aqueous. Yes? Lead is one of the exceptions for halides, just like silver is one of the exceptions. So that's why it's a solid. So that reaction does occur, and it makes solid lead chloride. Okay, number 16. Do we need to add or correct anything to our list of steps on question 13? We said determine all the cations and anions, swap them to see what compounds they might make. Maybe you want to add there to make sure that you balance the charges. Right, so that they make neutral compounds. Determine if these possible compounds produce a solid or a molecule. Maybe you want to add balance the reaction. So in question 15, I already gave you the coefficients to balance it, but let's just double check. 2 potassiums, 2 potassiums, 2 chlorides, 2 chlorides, 1 lead, 2 nitrates, and 2 nitrates. So again, I can't just put K with 2 nitrates. I have to balance the charge and then use the coefficients to balance the reaction. All right, so you now have a list of steps, and you've got 3 of these to work. These are the kinds of questions that you will see on a quiz. You're going to write a balanced reaction for each of these. If no reaction will occur, you just put NR. And when will no reaction occur? When you cannot produce any precipitate, no solid, or you cannot produce water. All right, so we'll do these one at a time. Pause the video and do question 17. All right, first I have the reactants, lead 2 nitrate and sodium iodide. I made the charges balance. Now you can complete and balance the reaction. If you didn't get these to start with, you can erase and try again. Pause now. So did you get these as your products? Lead 2 iodide means it needs 2 iodides to go with the positive 2 lead, and sodium nitrate. I have to split the nitrates up. 1 sodium is a positive, 1 nitrate is a negative. So I have this, and then I balance. Pause, and the balancing will appear in 2 seconds. I have a 2 here and a 2 here. Double check that everything is balanced. Now go on with question 18. Pause now. Okay, here are my reactants. Notice how I've told you that they're aqueous to begin with, so that saves you some time having to apply the rules. Ammonium chloride +1 and -1, potassium nitrate +1 and -1. The answers will appear in 2 seconds. So I swapped the partners, ammonium with nitrate and potassium with chloride, and when I apply the rules to those, they're both aqueous. So this is a situation where there's no reaction, because you cannot make a solid or water. All right, one more. Pause the video and do number 19. All right, so sodium hydroxide is a strong base. You memorized its formula. Sulfuric acid, a strong acid. You memorized its formula, so therefore they're both aqueous. And this one is a little trickier, but not that bad. What are the ions? Sodium and sulfate. So sodium and sulfate. But sulfate is a -2 and sodium is a +1. So I need 2 sodiums. And then the other one, H2? Ah, no, this is an acid. It splits up into H+ ions, and this is OH- ions. Well, what did we say H+ and OH- makes? When you combine them, that makes HOH, which is H2O. So sodium sulfate and water. Well, is sodium sulfate solid or aqueous? It's sodium. Most sodium compounds are soluble. I didn't leave myself enough room, so let's move this over. This is why I can erase, and if you use pencil, you can erase too. Water, is that AQ? If you put AQ, that means water surrounded by water. That's kind of silly. Water is just a liquid, right? And then we balance. 1 sodium, 2 sodiums. Oh, well, I need 2 out here then. All right? 2 sodiums is good. 2 OHs. And 2 OHs go with 2 H's to make 2 waters. I could balance the O's and the H's separately. 2 oxygens. There's 4 more oxygens, so that's 6 oxygens. There's 4 oxygens plus 2, that's 6. But it's just easier to balance the ions. And finally we have 1 sulfate, 1 sulfate. So there, that's balanced. Does this reaction occur? Yes, because it makes water, which is a liquid, so that makes this a neutralization. You could tell this happens because the reaction gets hot. When you mix sodium hydroxide and sulfuric acid together, it gets hot. This one, nothing will happen, no reaction. The one with the lead nitrate and the sodium iodide, that's a pretty commonly seen reaction, although it's usually done with potassium iodide. And just for fun, I looked up a video about lead iodide precipitating. I like this one. So this is the lead iodide. This is the lead nitrate, and this is the potassium iodide. And you notice that they are both clear and colorless solutions. And so now they're going to mix them together. And a precipitate of lead iodide is created. Sometimes they call it the lead iodide snow. It's kind of beautiful. But notice how quickly that reaction happens. Just as soon as a drop of the potassium nitrate, oh, that's the lead, let's see, what is that? That was the lead nitrate. They're dropping into the potassium iodide, right? And just as soon as that happens, the reaction is instantaneous, and it creates this precipitate. They do that one slowly so that you can see it. This one takes all of 10 seconds. Potassium iodide and lead nitrate, 2 colorless solutions mixed together, and boom, lead iodide, a yellow solid. If you then took that yellow solid that's precipitated and sort of weighted, the yellow solid would settle out to the bottom, hence calling it a precipitation, right? Just like precipitation, which is rain that falls out of the sky, that yellow solid would fall out of the solution. Okay. There's this last part of the activity which says that it's optional, about writing net ionic equations, and indeed, I'm not going to ask you to do that for this class. I'm going to go ahead and go through it because I think it's helpful for you to understand which ones are the spectator ions and which are not included in the what we call the net ionic equation. But I'm not going to ask you to do this on the quiz. Here's an equation which, if I read it out loud, says 2 silver 1 nitrates plus 1 calcium bromide becomes calcium nitrate aqueous and 2 silver bromide solids. This is a good exercise. If you split these out into the ions that actually exist, it's already balanced. So for 2 silver nitrates aqueous, that's 2 silver ions and 2 nitrate ions, which are aqueous. For calcium bromide, that's 1 calcium ion and 2 bromide ions. I move the 2 out into the front to indicate there's 2 bromides, and now they're separated, not connected. The same thing on this side. 1 calcium and 2 nitrates, but this one is different because silver bromide is a solid, and so even here I leave those together because that's a solid, and when they're a solid, they are not separated out into their ions, they're not dissociated. Alright, number 20. What is the product of the net ionic equation in Model 3? Alright, so here's the net ionic equation. Well, the product is silver bromide solid. What are the spectator ions? The spectator ions are the ones that do not change and are not involved in the formation of an insoluble solid. So which ones would that be? Well, that would be the calcium, which stays the same from the reactant to the product side, and the nitrate, which also stays the same from the reactant to the product side. So calcium and nitrate. See how that works? So if they don't change, they're not actually part of the reaction. If I just don't write them, then I end up with what's left over. Silver and bromide become silver bromide, and that's the net ionic equation, which is writing only the ions that actually are involved in making the bonding. So the silver and the bromide combine together to make silver bromide, but nothing happens with the calcium and the nitrate. They just stay dissolved in the solution. You can't see anything happening with them, and nothing is happening with them. You can do the same thing for number 22. Do them all if you like. I'll pause the video, and then all of these answers will magically appear. Pause now. Okay, and here are the answers. I'll just let you look at those and compare with your own. I did have to kind of squeeze the 2 chloride aqueous here. I was running out of space. But the net ionic equation includes only the barium and the sulfate, which make the barium sulfate solid. If you like, you can do number 23 as well. Pause the video and the answers will appear. Pause now. And here are my answers. Lead 2+ aqueous plus 2 nitrates aqueous plus 2 potassiums aqueous plus 2 iodides aqueous gives me 2 potassiums, 2 nitrates, and lead iodide solid, lead 2 iodide. This is the actual reaction that's taking place in the videos that we watched a little bit ago. The spectators are the potassium and the nitrate. You could say 2 potassiums and 2 nitrates if you like. And the net ionic equation is what you saw happening in the video. lead ions and iodide ions bonded together instantaneously to make lead iodide solid. So, you've got, as usual, some exercises to do. You're writing a balanced molecular equation. So the molecular equation is just when you write it like this, where it shows them, the compounds together, not separated out or dissociated into ions, including the phase labels. And there's A through F. Number 2 is where you do the net ionic equation for those. That's optional. You can do that if you like. It's good practice. It won't be on the quiz. All right. We're done with this activity. We're getting close to the end of Unit 3. Well done. It's time for me to take a nap. Cheers.